Okay, let us start again with another lecture, and the title of this lecture is Left and Right Limits. Let me start with another example that really asks for a different way to be treated, because we consider the sine function and we want to take the limit for x going to 0 of sine of x. We don't know what it is not easy to say what it is, and the function sine is the following. It is equal to 1 for x larger than 0, it is equal to minus 1 for x smaller or equal 0, and is equal to 0 for x equal to 0. So I write it precisely so you cannot complain at the end. And so we have sine of x, or SGN of x, is equal to 1 for x larger than 0, sorry, here it's x less than 0, minus 1 for x less than 0, and 0 for x equal to 0, just the definition. And now to compute this limit, and to show that it does not exist, just consider the sequence an, which is 1 over n, goes to 0, and the sequence of the images, sine of an, is equal to sine of 1 over n, which is always positive, so is equal to plus 1, constantly equal to plus 1, so it tends to 1. On the other hand, bn is minus 1 over n, it goes to 0 too, and sine of bn equal to the sine of minus 1 over n is constantly equal to minus 1, and this goes to minus 1. So, again, by the previous observation, by LTS 1, we have that the limit, the given limit for x going to 0 of the sine of an does not exist. Good. Very good. But here, in this example, you see that the situation is clearer than the previous example with the sine, or sine over 1, sine of 1 over x, because here what you have is that when you are at the right-hand side of 0, then the value you find is always 1. When you are at the left-hand side, the value you find is always minus 1, because you are here. So, instead of being concerned with finding the right sequences and so on, it is natural to distinguish between the right-hand side and the left-hand side. So, in this case, you may be tempted to say, that sine of x goes to plus 1 for x going to 0 and x larger than 0. Sine of x goes to minus 1 for x going to 0 and x less than 0, without using sequences. So, is this sufficient to conclude that sine of x has no limit for x going to 0? first question. The second question is much more difficult. Remember previous example with x sine 1 over x. So moreover, in the previous example, concerning the limit for x going to 0 of x sine 1 over x, we were able to conclude that x sine of 1 over x goes to 0 for x going to 0, x larger than 0, and x sine of 1 over x goes to 0 for x going to 0, but x at the left-hand side. So, is it sufficient to conclude further that the limit for x going to 0 of x sine 1 over x is equal to 0? The second conclusion is somewhat stronger because remember the LTS theorem says that the limit is true if and only if all sequences are mapped into sequences of images that go to 0. All sequences, not only sequences based at the right-hand side of 0 and at the left-hand side of 0, but also sequences that jump from one side to another. And of course, in this procedure, such sequences are excluded. So, is this true? It is sufficient to conclude in the first case the non-existence of limit, and the answer will be yes. In the second, if these two limits, one made from the left and the other made from the right, coincide, is this sufficient to conclude that the whole limit exists and coincides with the results that we found? And the answer is again yes. And this is the basis of the theory of right-hand side limit. Okay? So, let us go to define right and left neighborhoods, and then we will use it to define right and left limit. So the first definition is the following. Let x bar be a real number, then a subset of R is a right neighborhood of x bar if and only if in definition 1 just says if, there exists delta larger than 0 such that U contains this set here, x closed, x plus delta open, is a sort of half spherical neighborhood. So here we have x bar, and here we have x bar plus delta, good, and this is the set U, and U can have much more. The important is that it contains a right half spherical neighborhood that I will not define because it is quite useless. U must contain an interval like that. And so a remark, very simple remark, is that every neighborhood of X bar is also a right neighborhood of X bar. And of course, there are other comments to be made. So as in the case of neighborhood, of ordinary neighborhood, entire neighborhood, nor not right neighborhoods nor left neighborhoods, as in the case of ordinary neighborhoods. We have that every union of right neighborhoods is a right neighborhood. So remember what we said. For the ordinary neighborhood, every union means finite or infinite. First. Second, every finite intersection of right neighborhoods is a right neighborhood. And then we introduce the usual notation, the family of right neighborhoods, and this is U, as usual in sort of italics. X bar plus is the family of all subsets of R such that U is a right neighborhood of X bar. And now the definition of right limit. Again, we have a subset of R that will be our domain, and X bar an accumulation point, but such that for every right neighborhood of X bar, we have that the intersection of E with U minus the point X bar is not empty. What I'm saying here, it is important because I want to compute the right limit when X runs to X bar from the right. So in order to do that, at the right of X bar, I must find other points of the set E that are not X bar in every neighborhood arbitrarily close. I must be able to get arbitrarily close to x bar by remaining in E at the right-hand side of x bar. Okay, this is very important. Do you understand that? I'm saying a sort of this is not rigorous. I just give you the idea. X bar is a point of accumulation of E for the set E when coming from the right. Okay? This is not rigorous. Okay? The rigorous part is here. I ask you to understand this. Okay? It is the same as when we define the points of accumulation. The only difference is that here U is not a complete neighborhood. It's not an ordinary neighborhood, but it is just a right neighborhood. Okay? Then we say that the right limit of f as x tends or goes to x bar from the right. No, sorry, from the right. I already said the right. The right limit of f as x tends to x bar is L, or equivalently, f tends to the limit L as x goes to x bar from the right. We say this if n right lim of f of x for x going to x bar plus, with a plus, that means from the right, is equal to L, or f of x tends to L as x tends to x bar from the right, if for every epsilon larger than 0, but be more abstract, for every v in UL, L can be also plus infinity or minus infinity, so we use neighborhoods. For every v in UL, there exists a U in the family of right neighborhoods of x bar, such that the intersection of U with the domain E and with the only exclusion of the point x bar is mapped by F into V. Notice that this is the same definition. This definition is the same definition given for limits with the only replacement of the neighborhood of x bar with a right neighborhood of x bar. Notice only x bar, not L. Why not L? Because L can be reached from both sides. It is not a problem. L can be approached from below or from above. The point is that x goes to x bar from above, from numbers that are larger than x bar. Okay? And of course, we can give the very same definitions for for the left neighborhoods and left limit, and let me be quite fast with that, and let me reread what happens here. Let x bar in R, U in R is left neighborhood of x bar if there exists delta larger than 0, such that, and here for left is U, I do it in green, contains x bar minus delta x bar. Okay, the green is the left, and here we have x bar minus delta, and this time this is U, left. Every neighborhood of x bar is of course a left neighborhood of x, is both a left and right neighborhood. And again, as in the case of ordinary neighborhoods, every finite or infinite union of right, so of left neighborhoods is a left neighborhoods. Every finite intersection of left neighborhoods is a left neighborhood. And in the notation, what we have here is U x bar minus, and this is equal to the family of the U's that are left neighborhoods of x bar. Good. And the definition of left limit is exactly the same that we already know. And E in R, x bar in D, such that for every U in U, x bar minus, E intersection U minus x bar is different from 0. So we say that the left limit of f of x tends to x bar is L of f tends to L as x goes to x bar from the left. And right, here is x tends to x bar minus, x tends to x bar minus. And for every v in UL, there exists u in ux bar minus, such that, and this is the same, the definition is the same definition given for limits, with the only replacement of neighborhood of x bar with a left neighborhood of x bar. Okay, this is extremely simple. Okay, now before giving you the theorem that says that it is sufficient to study from the right and from the left, I will stop here, and then we will go to discontinuity, because studying left and right limits directly leads to the notion of discontinuity. Okay, see you.